Thanks to the organizers for the invitation. So as Victor Amunier said, I'm going to give an introduction to the Bures-Wasserstein Geometry, which is a particular case of optimal transport. And this is a topic I worked on with Marco, who was my PhD advisor at INSAE before I moved to Sierra a month ago. So this is meant to be an introduction. So please, if at any moment something is unclear, please ask maybe Victor, Emmanuel, or Thomas to ring a bell and let you ask your question. All right. So in machine learning, in data sciences, statistics, we often need to compare distributions. So let's say, for instance, we observe some discrete data, usually in the form of a discrete distribution. And what we want to do is to fit a model over it, so a parametric distribution or a neural network, right? And this is essentially what, for instance, generative modeling is about. So you have images, and then you want to fit a model that captures the distribution of the images so that you're able to produce new images. Okay, so to do that, we need a way of comparing those distributions, right? So we need a criterion to tell whether mu theta and nu are close to one another or not. So how can we do that? So essentially, from a bird's eye view, there are two ways of comparing distributions. So the first one would be to have a look at the vertical distances, if you may, between the densities. So you look at pointwise differences or pointwise ratios between densities, and you try to turn them into a divergence. So, for instance, you can define the total variation distance, which is, in a way, the supremum over those differences, the Kullback-Leibler divergence, which is a function of the ratios, or more generally, any type of F divergence, right? And this is a very powerful way of defining divergences that's very widely used in machine learning or in statistics. But in some cases, maybe you'd want to compare your distributions in a horizontal way. Like for instance, if we look at those two distributions, then from a vertical perspective, so according to total variation or divergences in general, they're pretty dissimilar because, well, at this point here and at this point there, the difference between the densities, the pointwise difference is very large, right? But that's not how we compare them when we look at them, because what we can see is that they're essentially the same distribution that's just been shifted, right? So is there a mathematical way to represent, to encode this way of comparing distributions horizontally? And the hope is that if we were able to find such a way, then we would have a divergence that would be better behaved when the supports of the distribution become disjoint, right? Because, for instance, in that case, if you take an F divergence, then basically you have no information on the distance between those two distributions, because no matter how far they are from one another, you're going to get the same results. Okay. So essentially, optimal transport is exactly this. It's a way to compare distributions according to horizontal distances distances between the points on the supports of the measures. So optimal transport was defined by Monge in the 18th century, and so Monge observed workers that were doing earth-moving works, and so they had some pile of dirt or earth. They had to move people. And the question Monge asked is, how can they organize themselves to minimize the total effort they have to produce to do that? And the way he measured this total effort is by taking the total sum of the square distance the workers travel times the quantity of mass they transported along that distance, right? And you take the sum of this, so the integral of this, and you get the transportation cost, okay? So what you need to find is a map that says where you send the mass of each that's contained at each location x in the pile of dirt mu, the measure mu, to the hole in nu, t of x, okay? So you want to find a map that minimizes the overall transportation costs. And what you can see is that obviously you cannot take any map because your map has to transport nu to nu, meaning that at any location t of x, the quantity of mass that's present must be equal to the quantity of mass you picked up at x, right? There's no mass that can be created or deleted along the way. And so mathematically, you account this by saying that the measure of any, the mass of any set A according to nu must be equal to the mass of its preimage by t according to mu. Or in other words, another way of seeing that is that if x is a random variable that's distributed according to mu, then t of x has to be distributed according to nu. And if t satisfies this condition, we say that t pushes forward mu to nu, and we write t sharp mu equals nu, which means that t transforms mu into nu in a sense. And so Monge's problem is to find the map that transforms mu into nu that has the lowest transportation cost. And in this talk, we're going to focus on the case where the cost is defined by, the ground cost is defined by the squared distance. And in that case, this optimization problem here defines the two Wasserstein distance between distribution, and it's an actual distance, a metric in the usual mathematical sense, meaning that it satisfies all three metric actions. Okay. So now that we've defined optimal transport, let's check whether it satisfies the intuition we had that it should encode horizontal distances compared to vertical distances. But if we look at the interpolation in optimal transport sense compared at the interpolation in Euclidean sense, then we can see that it actually does this, meaning that optimal transport corresponds to comparing distributions according to the distances on the supports, whereas Euclidean or F divergence interpolation or divergences correspond to comparing pointwise differences between the densities. Okay, so optimal transport seems great, but can we compute it in practice? So the answer is a bit complicated. Essentially, it depends on the type of distribution we're considering. So we're going to take two cases. We're going to assume our distributions can either be continuous, meaning that they have a density, or discrete, so that they can be written as a sum of directs, a weighted sum of directs. So if both the distributions are discrete, then we can solve the Kantorovich relaxation of optimal transport using linear programming in times n cubed log n, where n is the number of directs in the distributions, or we can approximate it using entropic realization. If one distribution is discrete and the other continuous, then it gets a bit more complicated. We have to do approximations on grids or stochastic approximation. And if both distributions are continuous, then it's very difficult. In low dimensions, we can make links with variational problems or PDEs. This is very expensive to solve. And if the dimension gets high, then essentially there are two options. The first one is to use some kind of parametrization for the potentials of the maps, for instance, using neural networks, or to model data such as to fall back to closed forms. And there are essentially two cases of closed forms. The first one is optimal transport on the one-dimensional line. And the second one, which is the one that's going to interest us in this talk, is the case of Gaussian distributions and elliptical distributions, which are a generalization of Gaussian distributions. Okay. So look at optimal transport for Gaussians. So we saw that in the case of continuous distribution, there were basically nothing we could do apart from some very specific cases, which were Gaussian or atypical distribution. And so let's just dive into this. So if we have two measures of the Gaussian distributions, then the Wasserstein distance, so the optimal transport distance between these Gaussian distributions, can be decomposed as a term that corresponds to the distance between the means of the distributions and a term that corresponds to the distance between the covariances, the covariance matrices of the distributions, right? And this distance between covariance matrices is called the Bures distance for positive semi-definite matrices. So the Bures distance, so this distance that's written right here, it's a distance that's defined on the cone of PSE matrices, on which it defines a Riemannian metric. And so it's the sum of the traces of A and B minus the trace of this matrix square root, which is a bit scary. So let us look at some particular examples to see how it can behave. So first, what we can see is that if A and B commute, so if we take two Gaussians that have the same axis, same principal axis, then the Bures distance is just the Frobenius distance between the matrix square roots, the square roots of the covariance matrices, which is sometimes called the Hellinger distance for matrices or for vectors. If the covariance matrices go to zero, then the Wasserstein distance, so the Bures distance already converges to zero as well, and the Wasserstein distance between our Gaussian distributions goes to the distance, the Euclidean distance between the means, which is also the Wasserstein distance between Diracs supported on these means. So what we can see is that in the case of Gaussian distributions, the distance remains geometrically meaningful even if we have degenerate covariances that go to zero. And the expression above of the Bures distance remains defined even in the case of singular matrices, meaning that we can also compare Gaussian distributions that are supported on lower dimensional subspaces and not necessarily on the whole space, which is something we cannot do using, for instance, the Kolbe-Fiber divergence. Okay, so if we look at optimal transport between Gaussians, we have a closed form distance, but it does not end here because we also have a closed form for the optimal transportation maps. And those maps are actually affine maps that are defined in closed form according to, as a function of the covariance matrices of alpha and beta. Okay, so we have closed form distances, and we also have closed form transportation maps, and those transportation maps are affine, so they're very simple. And actually, from those transportation maps, we can also derive the Riemannian geodesics between the covariance matrices, so the Bures Riemannian geodesics, which are also the Wasserstein Riemannian geodesics for a Gaussian distribution, right? So to wrap it up, in the case of continuous distributions, there are very few results. One of the cases where optimal transport can be used in practice is Gaussian distributions, for which we have closed form distances, we have closed form transportation maps, and we even have closed form geodesics, right? So it seems like the Bures-Wasserstein distance geometry is a very promising distance in geometry for machine learning applications. Maybe you can use it in machine learning.
Boris, can I ask you a question?
Yeah.
Yes.
Sure.
So in the previous, yes. So if you say if not invertible, use pseudo inverses, but there is no transport map, right? If A is not invertible.
Yes, okay. So if they're not invertible, then the transportation map is defined as long as the image of B is included in the image of A, meaning that you can restrict the maps, but you cannot do the opposite because it's a map, right? So
okay,
yes,
I see.
Okay, so yes, for simplification, I wrote this, but yes, you're right. We can define couplings if this condition is not satisfied, but if it is satisfied, then we can find maps from A to B, but not from B to A.
Okay, and there is a closed form formula that is simple for the couplings in the general case?
Well, if either the image of B is included in the image of A, or the image of A is included in the image of B, then yes, because the coupling, you can define the coupling with either the map from A to B or the map from B to A. Yes. But if none of those assumptions are satisfied, then there definitely, most probably is a closed form for the couplings, but I can't remember it just right now.
Okay, thank you.
But and the same condition applies for the geodesics actually, obviously, because you can go from A to B if the image of B is included in the image of A, but you cannot go in the opposite direction using the same closed form. Okay. And actually, it so happens that those closed forms, the closed form for the distance, for the Monge Map, from the geodesics, are not only valid for Gaussian distributions, but essentially, morally, for any distribution that has elliptical level sets. Meaning that, so if you look at the density of a normal distribution, then it's written like this. So there's the covariance matrix, the means, and it has the density has this form. So it's G of this Mihalanobis norm. And in the case of Gaussian distribution, G is exponential minus x over 2 divided by something to make it integrate to 1. But we can replace G with any positive function that integrates such that this term here integrates to 1, and we have the same closed forms. So same expression of the Wasserstein distance as the sum of the distance between the means and Bures distance, same Monge maps, so on. And we can go even a step further. We can consider the case of degenerate distributions by replacing the inverse of A with a pseudo inverse, and the density in that case won't be defined as a density with respect to the Lebesgue measure, but a density with respect to the Lebesgue measure on the image of A, which is a near subspace. So those results were proven by Gelbrich in 1990. And as an example, this means that we can have closed form for the Wasserstein distance between, well, for instance, direct measures, which is just a case where A goes to 0, for uniform measures over ellipsoids that can be degenerate or not. So, for instance, a segment is an ellipsoid. So essentially anything that has an elliptical level set. So as an illustration here, I've represented so 1, 2, 3, 4 ellipsoids endowed with a uniform measure that have the same distance to this reference ellipsoid A according to the Bures-Wasserstein distance. So they can be, so here's a direct, this is an ellipsoid, it's just a line, etc. So the Bures-Wasserstein distance in that sense is very flexible as it does not require your distributions to have full support. Okay, so we saw that we had closed form distances, closed form transportation maps, geodesics. We could apply it to anything that has an elliptical level set, even if it's degenerate. So can we actually use it in machine learning? Meaning, can we do gradient descent with the Bures-Wasserstein distance? So if we take a step back, well, in machine learning, most applications can be cast as minimization problems. So we want to minimize some loss function, an expectation according to some distribution, and try to minimize some parameter. And usually the way we optimize this parameter is by using some kind of variant of gradient descent. So it can be stochastic gradient descent, gradient descent of momentum, or we can even go one step further and use second order information. So could we do this with the Bures-Wasserstein function distance as a loss function? So for example, let's say I want to solve this minimization problem, which is just a barycenter problem in the Bures-Wasserstein distance. What I need to be able to solve this problem using gradient descent is, first, I need to be able to compute the Bures distance between my parameters. I must be able to compute the gradients of the Bures distance, and I must be able to do gradient updates, which might seem a little trivial, but actually, since I'm working with covariance matrices, those matrices must remain PSD. Okay, and if I can do all of those three things, then I can move on to a more complicated problem using the chain rule and backpropagation to minimize functions of the Bures-Wasserstein distance. Okay. So first step, I need a method for computing the Bures distance and its gradients. So here I've recalled the expression of the Bures distance. And so the first idea we might have to do that is to compute the matrix square roots using singular value decomposition and maybe backpropagate through singular value decomposition, as this is possible frameworks, machine learning frameworks, to compute the gradients. So this works, but it has several drawbacks. The two main being that singular value decomposition is expensive, and we need two of those because we need to compute the square root of a, and then the square root of a times b times the square root of a. And the second drawback is that differentiating through SVD can be quite unstable if we have non-distinct singular valuing because we have branching effects, or if our matrices are singular, whereas the Bures distance and the Monge maps remain defined in some cases. So maybe we're losing something here. So we'd like to find a better method to compute the Bures distance and its gradients. Well, actually, if we look a little bit closer at the Bures distance, then we can see that we can actually compute it as a function of the transportation map. Indeed, if you look at the expression of the transportation map and you plug it back here, then those two trace terms are equal. And so if we have access to the transportation map, then we also have the Bures distance up to matrix multiplication and the trace. And what's more, if you take the gradient of the Bures distance with respect to its parameters, then you can show that it can also be expressed as a function of the Monge map. So if we want to compute the Bures distance and the gradients with respect to A and with respect to B, all we need is a method to compute the Monge map from A to B and the Monge map from B to A, which is the inverse of the Monge map from A to B. So if we have all we need is an efficient algorithm to do that, and that's it. We can compute the distance and the gradients. Well, it turns out that such an algorithm exists, and it's called the Newton-Schulz iterations. So those are actually iterations that are designed to compute the matrix sign function, and with particular initialization, they converge quadratically to the Monge map from A to B and the Monge map from B to A. Okay, and they only involve matrix-matrix products. So compared to singular value decomposition, they have essentially two advantages. The first one is that they're super easy to parallelize on GPUs because they require only matrix multiplications, and I can even compute distances in batches because I can do tensor products on GPUs very easily. And they yield simultaneously the Monge map from A to B and the Monge map from B to A, meaning that if we run those iterations, once we get the distance and both gradients. Okay, so this is super nice. So we have a method to compute the distance and the gradients. So let's compare this to a singular value decomposition. So if we're running it on CPUs, what we see is that for low dimensions, it doesn't make such a big difference to use Newton-Schulz or singular value decomposition, because the dimension increases and the cost of Newton-Schulz blows up way faster than a singular value decomposition. But on the other hand, if we're using GPUs, then the opposite happens, and it becomes way more efficient to use Newton-Schulz iterations. And this even the more so as Newton-Schulz iterations, we can compute distances and gradients and batches with SVD. Okay, so we have our first two requirements, meaning that we can compute the distance and its gradients. But now we need to be able to do gradient steps. Indeed, there's a last remaining issue, which is that if I take a parameter, a covariance matrix, and I update it using a gradient update, then the result is not necessarily a positive semi-definite matrix. It's going to be symmetric, but not necessarily a positive semi-definite. So the first option would be to do projected gradient descent. So I take this and I project it back on the cone of PSD matrices. But this requires to do a singular value decomposition, and which is something we'd like to avoid because it's a bit expensive. So we'd like to find another way to do that. And another classic workaround when we work with PSD matrices is to use some kind of a Bourrier-Montero reparametrization. And instead of working directly with matrices A and B, we're going to take some factorization. So we're going to write A in LL transpose form, and we're going to optimize with respect to the parameters LA and LB, which are not necessarily the Cholesky factors, by the way, just any parameter that is such that LL transpose equals A, okay? And so if we do that, then if we optimize with respect to LA and LB, then we don't have to project on the PSD cone because LA transpose is going to be PSD all the time. But a natural question is what impact does this have on gradient descent, right? Do I gain or lose anything by changing parametrization? And what we've showed with Marco is that, in a sense, working in this LL transpose parametrization allows us to mimic Riemannian gradient descent at the cost of Euclidean descent. And what I mean is that if you look at the gradient of the Bures-Distance with respect to this parameter, and you plug it back into the gradient update, then we can show that doing a step of length t, a gradient update with step size t between 0 and 1 is the same thing as taking a step of length t along the Riemannian geodesics between A and B. And this is really remarkable because there's a whole field of optimization, which is called Riemannian optimization, in which people try very hard to approximate Riemannian geodesics to perform geometrically meaningful optimization. And in our case, in the Bures-Wasserstein case, we get this for free simply by using this parametrization. Okay, so to wrap it up, we have closed form distances. We know how to compute them efficiently on GPUs. We know how to compute the gradients. We can do gradient descent without projections. And this gradient descent actually mimics Riemannian geodesics. So it seems like we have everything we could dream of to do some machine learning. And so now I'd like to present a few applications. And so the first application I'm going to present is an application to representation learning. So the problem of representation learning is that of finding representations, tractable representations, or some objects that live in some space of that can be, for instance, a high-dimensional vector space, but also the space of words or graphs. So it's a very generic problem. So we can assume that we have structure on objects, or assume that we don't have any structure, right? And what we want is to find some representation that's going to be tractable in the mathematical. So the classic approach is to represent each point, each object X as a point in a low-dimensional vector space. So which is what we do when we do MDS or t-SNE or those kind of methods. And what we propose with Marco is to, instead of representing each object as a point, represent each object as an elliptical distributions, which means that instead of learning just a single point, we're going to learn a point that's going to be a mean parameter and a covariance matrix using the Bures-Wasserstein geometry. And the reason we might want to do that is that by using this parametrization, we hope that we're going to get representations that are going to allow us to encode richer information on our objects. So in the example of word embeddings, so here, so we see that we have a in the form of translations. If we use representations, then not only do we get the points, but we also get the covariances, which allow to encode a different type of information, such as spread or uncertainty. For instance, in this example, it seems very natural that the representation of man is much wider than the representation of a composer, because a composer is a more narrow word than man. And so we implemented this method by, we implemented the training of elliptical word embeddings by taking the objective function of that are used to train word embeddings in the usual way, so between vectors, and replacing everything Euclidean with Bures-Wasserstein counterpart. In doing this, we showed that we obtained embeddings that were very competitive with respect to the 2018 state-of-the-art on similarity benchmarks and on benchmarks of NLP that are a bit more specific, but that represent some hierarchical relationships between words. Okay. And second example of applications to machine learning is the definition of a quality score for generative models. A problem people have in the generative modeling community is how to assess whether your GAN produces outputs that are similar in terms of distribution to your ground truth dataset. And a method that was proposed by Haussel and co-authors in 2017 is to use the Bures-Wasserstein Distance, which we call the Fréchet distance because they base themselves on indifferent references, between the mean and the covariance of the inception features. So what they do is they take samples from their GAN and samples in their ground truth dataset. They feed them through a neural net, an inception neural net, and they extract not the last feature, but the one just before that, which is a layer of size 2000. So they have features of size 2000. They take the mean and the covariance of those features, and they compute the distance between those mean and those covariances using the Bures distance. And what they show is that this criterion, even though it only uses means and covariances of those features, allows to quite efficiently predict whether assess whether your GAN produces outputs that are similar to that of your datasets. Okay. And so finally, I'd like to conclude my talk with an opening for people that are maybe a bit more familiar with optimal transport. So in the real world, data comes in a discrete form, meaning that we observed data sets that are like observations of a given distribution, and we can build an empirical distribution from it. But then if we want to work in an optimal transport framework, then we have several options. So the first one is to keep our distributions as such and compute optimal transport without any form of regularization, which has several drawbacks, the main one being that it's very expensive. But if we want to alleviate this problem, then we have two options. The first one, and maybe the most widespread, is to regularize the problem by adding entropic regularization, which defines the Sinkhorn divergences, for instance, or we can even relax the marginal constraints and get unbalanced transport, and this alleviates the cost. And the other orthogonal direction we can take, which is the one I've shortly presented, is to, in a sense, regularize the data, meaning that we use some modelization that's going to be tractable. So, for instance, if we use a representation in the form of elliptical distributions, an optimal transport is the Bures-Wasserstein distance, and we have closed forms. But then a nagging question is, what is there at the intersection of both approaches? Like, can we both regularize the problem and the data? And this is something we've explored with Hicham, Marco, and Gabriel Perret at last year. And so we showed that if we regularize the optimal transport problem by adding entropic regularization and even by relaxing the marginal constraints, then we still have closed forms. And this provides for the first test cases for entropic optimal transport and unbalanced entropic optimal transport between continuous distributions. And so this is a paper that's going to be presented next Wednesday, so in 8 days at NeurIPS. So if you're interested, please come see our oral on Wednesday at 3:15 or meet us at the poster session. So thank you for your attention, and I'm happy to take your questions.
Thank you very much, Boris. So we have 5 minutes for any questions. So please feel free to turn your microphone on and just ask. So okay, I will try. I will start with one question. Maybe I didn't understand. In your gradient descent procedure, do you use this Newton-Schulz iteration?
Yeah. So actually, the Newton-Schulz iterations they're just used to compute the distances and the gradients because they're allowed to compute the Monge maps. And from the Monge maps, we can get the distances and the gradients.
Okay. Yeah. And how restrictive is this assumption to get quadratic convergence? You see, I mean, this identity minus this block matrix. Yes.
Oh, actually, it's not restrictive at all because to satisfy it, you only have to divide B and A by 1 plus epsilon times their norms, and the Monge maps actually are homogeneous with respect to A and to B. So you just have to divide A and B so that this condition is satisfied, and then you multiply back to get the Monge map between A and B before you divide it.
Oh, okay, that's great.
Yeah, because what we mean by quadratic convergence is that the distance between the iterations satisfies this condition, right? And so you only guarantee. So this only guarantees that you'll have a convergence if you're already way below 1 here.
Yes. Mm-hmm. I see. And one other question that is it's very theoretical and not very useful. But so you said that. So we have closed form formula for the transport map and for the distance between elliptic distributions. And an elliptic distribution, so it's a distribution whose density has the form some function of the Mahalanobis norm of x, right?
Yeah.
So yes, so x norm sub a of x, or norm sub a inverse of x. Now, instead of taking an ellipsoid, if you take a symmetric convex body, so you take the norm associated to the convex body, which just means that the density will have its level sets that will be homothéses of a given symmetric convex body. Can you, I mean, are there some formulas, or is there anything you can do in that case?
Okay, this is an interesting question. So I'm not sure what the norm here would look like, but so essentially the reason why it works so well in the case of elliptical distribution is that when you apply it's because we have those geodesics, right? So which means that if you apply the map from an elliptical distribution to another, that at any time along the way, you're going to be in elliptical distributions, right? Yes. Which is something that's very particular. So if you can show this for your example, relax to convex bodies, then there's something that can be done, I guess.
Okay, because I don't know if the same will be true, but at least maybe because here what's interesting is that the distance between two such elliptic distributions does not depend on G. It only depends on this Mahalanobis norm.
Well, so there's just there's just one thing, which is that this is true only if you have the same G on both sides, right? You cannot compare.
Yeah, of course. Yes. Yeah, absolutely. But if you still have the same G on both sides, but instead of having such a Malar-Novice distance, you have a norm that depends on some convex body. Will the distance between two such distributions with the same G but different convex bodies depend only on the convex bodies and not on the function G?
Yeah, that's interesting. Yeah, I guess maybe I think if you could show that there's a type of maps that transforms your a generic type of maps that transforms your convex bodies from one to another, which is the case, for instance, for the linear maps and covariance matrices. So the TAB here, if you multiply TAB times A times C is B, then you get B. And so if you get the equivalence for convex bodies, then it might be, maybe not in a linear form, maybe it's going to be a more complicated function. And if you get this, and if you show that this map is a transportation map, that yeah, it might be possible, I guess.
Okay. Okay. Thank you very much.
You're welcome.
Hi, I have a question. Is it possible?
Yes, of course.
Yes. So thank you for your presentation. I've heard some critiques about using a Wasserstein distance with learning continuous distribution due to the Dirac comb, the Peine de Dirac. Have you ever heard these critiques, and do you agree with them?
Sorry, I didn't get to the Dirac what?
The Dirac comb, le Peine de Dirac, approximating continuous distribution with discrete view in order to compute Wasserstein distance.
Okay, so I think you're referring to the fact that you need an exponential number of Diracs to approximate your.
Totally,
okay, yes. Yeah, you're right. This is definitely an issue, but this issue can be alleviated if you, instead of considering the original Wasserstein distance, if you add some entropic regularization, then you can show that the problem partially goes away, because instead of having an exponential complexity, you get the complexity in terms of the number of Diracs you need to approximate your measure. You get something in 1 over square root of n, but the constant is also exponential with respect to the dimension, right? But I agree that I think if you want to learn a continuous distribution from Diracs directly, then you shouldn't use the Wasserstein distance. Sorry, directly. You should either regularize the optimal transfer problem or regularize the data in a sense. So if you, for instance, if you were to, you could take your Diracs and then from those Diracs estimate a Gaussian distribution, for instance, and then use the closed forms to do that. But I think that if you want to do it directly, then you can't really escape the curse of dimensionality. Yes.
Okay, thank you.
Right. So thank you very much, Boris.